Next, we have Dr. Christian Sestito from April. I'm going to say that right, otherwise it's very long. Christian is going to talk to us about TrIM, which is an efficient systolic array for convolutional neural networks.
So, let's check. So, thank you so much, Gareth, for the introduction. Yes, I'm research fellow at the University of Edinburgh, and today, yes, I will guide you through towards this new systolic array architecture that is taught for convolutional neural networks. So, first of all, we will start with some basics about convolutional neural network and some application fields that benefit from those type of AI models. And then we will go through the hardware architecture that usually accommodates such workloads, so spanning computer architecture, and in particular focusing on systolic array. And eventually, let's say I will conclude the discussion introducing this new architecture of systolic array, how the data moves. So what is the data flow? What is a potential architecture to accommodate such data flow? And what are the results also compared with the state of the art? Now, first of all, convolutional neural networks, in a way or in another, mimic, let's say, the behavior of the human visual system. So basically, our eyes grab information from the input images, and our, let's say, brain process those data in order to extract features of interest from the images. And the convolutional neural network work in the same way. So basically, they consist of a sequence of convolutional layers that basically consists of kernel of weights that are responsible to identify specific patterns from data, starting from, let's say, low-level features like shapes, edges, and moving towards higher, let's say, level of abstraction in terms of features, so complex objects. Eventually, there is a classification layer that usually consists of fully connected layer that perform matrix multiplication in order to finalize the classification task. As an example, in this case, we have a digit represented in the image, and the goal of the convolutional neural network is to identify the specific digit that is visualized. Now, let's go a bit into the specific of the functionality of convolutional layers. So basically, convolutional layers, the input space is represented by a set of feature maps that we can think as a sort of images. And in this set of feature map, we have some three-dimensional filters consisting of multiple kernels that scan each feature in raster order. So from the top left to the bottom right. Basically, for each scanning that the kernel is performing, we have multiply accumulation between the weights of the kernel and the activation, let's say the pixel of the image. Finally, let's say the intermediate results that come from each feature maps are accumulated in this space direction, that is the channel direction, in order to get the pixel, the activation, composing the output feature maps. Finally, it is worth underlining that, let's say, each specific three-dimensional filter is responsible of the generation of a specific unique output feature map. Now, convolutional neural networks have found in the last, let's say, 10 plus years, application in a wide spectrum of tasks, ranging from computer vision to autonomous system to other type of approaches. As an example, in computer vision, other than image classification, we have application in image segmentation, face recognition, and medical imaging, satellite imaging. In autonomous system, convolutional neural networks are heavily applied in autonomous vehicles, as an example for lane detection purposes or for traffic cycle recognition, as well as in robot activities like path planning. Finally, convolutional neural network also find application in a task like time series analysis, recommendation system, drugs, material discovery, and so on. Now, CNN by default are, let's say, models that require huge computation and say lot of memory in order to complete in a successful manner the given task. For this reason, it's imperative to allocate such model in dedicated hardware accelerators. So traditionally, we have two types of architectures. From one side, temporal architecture, and from the other side, spatial architecture. While temporal architecture consists of a lot of arithmetic logic units that basically are centrally controlled, as well as also the memory hierarchy is central. In spatial architecture, let's say there is a communication between the arithmetic logic units. And in addition, the control and some levels of the memory hierarchy are pushed at the boundaries close to each arithmetic logic unit. We might say that we pass from conventional ALU to processing elements. Why these movements toward the spatial architecture is beneficial for the field of, let's say, hardware accelerator? Because of this figure. Usually, in terms of energy, the highest impact, let's say, in a system is targeted by the memory itself. As you can see, let's say, a DRAM memory access, it's orders of magnitude higher than simple operations. So it is imperative to try to reduce the communication with the, let's say, high level of the memory hierarchy and try to push the majority, let's say, of the communication at the boundaries of the computing units. Systolic array stay in this area, in the area of the spatial architecture. So the concept of systolic array was conceived at the end of 1970s. Those consist of a class of parallel computing architecture that basically consists of a matrix of processing elements. And basically the term systolic refer to the synchronously of the data that move between processing elements. In a way or in another, they mimic the behavior of human blood while flowing throughout, let's say, the body. For this reason, they were labeled in this way. However, between, let's say, the late 1970s to 2015, the interest about those type of architecture was fairly moderate. Finally, in 2015, Google proposed the tensor processing unit, well known, that basically at the core level include a systolic array. In particular, the first version of the tensor processing units included a 256 by 256 systolic array. Starting from that point, the interest became more significant, both in academia, but also in industry. Now, according to the way in which data moves throughout this type of architecture, we may classify systolic array under different classes. We have weight stationary, output stationary, input stationary, row stationary systolic array. Just to provide an example to understand what this means, let's consider the weight stationary. In the weight stationary systolic array, what happens is that the kernels of the convolution, so the weights, are located in each processing element as long as they are required. This means that we store those values and that type of data movement is nullified. We don't need anymore. The other type of data, so the input feature map activation and the partial sum, move synchronously throughout the array. As an example, input feature map may move horizontally, while partial sum may be moved vertically. This is just an example to identify why the specific stationarity identify a given type of data. Now, systolic arrays themselves are naturally conceived to perform matrix multiplication. However, the convolutional workload, since manage images that are scanned in raster order scan, so from top left to bottom right, this strategy, the computational strategy, is slightly different. What is happening, I would say, what happened in literature in the past? People said, okay, let's try to uniform the conventional matrix multiplication and deconvolution. So let's transform convolution as matrix computation. So in this way, we may use a type of systolic array and we don't need to prepare a sort of bespoke accelerator. However, there is a main problem, and the problem is dictated by the significant data redundancy. When transforming convolution in matrix multiplication, we have a lot of repetition of data that results in memory transaction that we cannot get rid of. So for this reason, it is important to dedicate bespoke accelerator for the convolutional workloads in order to maximize the data utilization at the boundaries or inside the systolic array. For this reason, let's say, we recently conceived a new type of data flow, specifically tailored for convolutional workloads, that is TrIM. TrIM stands for triangular input movement. Why? Because basically the movement of the input feature map activation in this case is exhibited through a triangular shape. In particular, inputs are first provided vertically from the main memory, then they locally move horizontally from right to left, and then, when needed, they are reused to diagonal movements. So at the end of the day, we get a triangle. Now, in order to understand how this data flow works, let's consider a very basic example. Before the example, this is just a schematization of the processing element. So the module that performs the single computation inside each block. So basically, we have a multiply adder unit, as well as some registers in order to synchronize the data properly, and some multiplexer logic in order to identify the direction through which the specific type of activation flows. Now, let's consider a basic example in which we have a 3x3 kernel and a 5x5 feature maps with the objective to generate a 3x3 output feature map. So, in the very first instance, before any computation, the weights are preloaded. So in this way, we may say that TrIM, in terms of stationarity, mimic the weight stationary systolic array. So we block the weights at the processing element level, and we keep them stored as long as we need. After this, we may start the actual computation. First of all, we inject the first row of 3 elements, 1, 2, and 3, that are multiplied by the respective weights, A, B, and C. This is realized through vertical movements highlighted in blue. In the second, let's say, step, in the second clock cycle, I would say, we continue the computation of the first window of kernel by, let's say, injecting the activation 6, 7, and 8 that are summed to the previous results that were computed in the previous cycle. At the same time, we start computing the second window, so the activation 2, 3, and 4 with the weights A, B, and C, as you can see in the very first row. In this case, while here we are having injection from external and while partial sum are moving vertically, the activation, let's say, 3 and 2 were moved from the previous cycle through horizontal movements. Thus, let's say, shifting the data movement inside the systolic array. Third cycle, we finally are able to finalize, let's say, the computation associated to this window in red, as you can see by this dot, by injecting the new data from external. And in the meantime, we are able to further the execution of this window through horizontal movements and also initiate the third window on the top by injecting, let's say, this activation from the external and moving the other through to horizontal movement. Finally, in this cycle, we're able to identify the last type of movement that finalize our triangle, that are the diagonal movements. Okay? In order to support those type of movements, some extra register placed at the boundary of the array may be necessary. And usually this depends on the size of the input feature map that we are considering. And this process continues in this way till the end of the convolution. So after an initial latency, let's say we are able to provide one valid result per each clock cycle. I forgot to mention that in order to successfully finalize the convolution, the final partial sum that sits at this level are finally reduced through an XR adder tree, in this case consisting of only 2 adders. Sorry. The pointer is not working.
Yeah, well, it's not shared. I just want to share it. You can't see it anywhere. Shared.
Sure you're not next door?
It's shared.
You sure you're not supposed to be next door?
It's 1 or 3. I don't know. Try again.
Thank you so much.
Sorry.
So,
This way or that way?
while the previous one was just an example to show very simplistic toy case to understand the data flow, this is the type of generalized architecture that is, let's say, flexible to accommodate a generic input feature map size. In particular, the main difference with the previous example is the presence of a shift register buffer whose size, let's say, is dependent of the input feature map. This shift register buffer is reconfigurable. In this way, throughout you move inside a convolutional neural network, you are able to runtime adapt, let's say, the capability of the systolic array to manage input feature map images of different sizes. Now, in order to manage multidimensional convolutional layer, as usually happens in the reality, let's say the specific type of module is just a slice that is integrated at the system level. Those slices are furtherly reduced by other trees in order to get the results of the current feature maps. And in order to generate more output feature maps in parallel, this specific unit is parallelized in a TrIM core fashion with the present with some partial buffer in order to orchestrate properly the data splitting over the time. Now, as I was saying, the main point, let's say, of implement those type of systolic array was to improve the memory access in terms of, let's say, convolutional workloads. In this case, we are comparing two state-of-the-art neural network, the PGG16 model and the AlexNet model that are very famous model for classification, comparing TrIM with Iris. That is a very famous systolic array architecture that has been conceived in 2015 in the US. And as you can see, TrIM outperformed this previous systolic array under different type of configuration workloads in terms of memory access. In the PGG up to, let's say, 5 times, and in the AlexNet up to 8 times. Finally, we implemented this accelerator on FPGA in a Zinc ultra-scale architecture. And when compared to very recent state-of-the-art work, we have noticed a competitive results in terms of giga operation per second throughput, and also a competitive result in terms of energy efficiency, so giga operation per second per watt. So finally, as we said, convolutional neural networks are very well-known models in order to behave as feature extractors, so extracting feature at different level of abstraction. But accuracy, operation, and memory is an important trade-off to consider. For this reason, systolic array are promising candidates to tackle the data communication between the computing core and the memory, the well-known von Neumann bottleneck. And in particular, with TrIM, we maximize the input feature map utilization locally through this new triangular movement. And when compared to the art, we have reduced memory access overall. So I acknowledge for this work the support of the EPSERC Forte program, the Royal Academy of Engineering Chair in Emerging Technologies, and the April AI Hub. So thank you all for your attention.
Probably one question, if anyone has. If not, please catch
Okay.
Christian afterwards.
Thank you.